Okay, so last time we learned about two-body systems and drawing free body diagrams and solving net force equations with them to find the acceleration. We're going to do something similar this time, but we're going to make it a little bit more complicated. The experiment is repeated, but on a table that is not frictionless. The coefficient of kinetic friction between the table and m1 is mu. Determine the acceleration of m1 in terms of m1, m2, mu, and g. So this time, we're adding in that the table is not frictionless, as it was last time. But other than that, nothing else really changes. So our assumptions are going to remain the same as last time. We're going to assume that the tension in this string is the same at all points. That doesn't mean it won't change ever. It just means that at any point in time, the tension is the same here as it is here. Okay, that doesn't mean all tension in every string is the same. Just in this one particular situation, the tension is the same throughout the string. We're also going to maintain the assumption that the acceleration in both the acceleration of the system. Remember, our system is m1, m2, the string, the pulley, and I guess this time it has to include the table. The acceleration is constant, or the acceleration is constant for each part of the system that is moving. Okay? So our first step is to draw free body diagrams for our objects. This should be pretty easy. We'll do m1 first. Here's m1. Might as well keep our standard axis, x, y, positive. We see that we have tension pulling the m1 to the right, so that's T. It's resting on a surface, so normal force points straight up. It's a flat horizontal surface. We have a force of gravity pulling back, or not force of gravity, excuse me, force of friction, this is nu, pulling back on m1, resisting that motion that would otherwise occur. And we have the force of gravity. Don't know why I wrote F1, should be Fn. And this is FG1. For M2, we have the same exact free body diagram as before. But remember, we're tilting our axis so that x is in the down direction. Positive x is down. And again, the reason for that is if M1 moves to the right, that means M2 must have moved down. And if M2 is moving down and M1 is moving to the right, we might as well make those our positive directions, since one can't happen without the other. Positive x directions, I should say. We have, pointing downward, Fg2, force of gravity on object number 2, and tension pointing up. And we don't need T1 and T2 because we know the tensions are the same. Now it's time to write our net force equations. Let's do M1 first. In the y direction, we have Fn minus Fg1 equals M1ay. Again, M1 does not look like it's going to suddenly accelerate up off the table or down into the table. We can therefore conclude its acceleration is 0. And that Fn equals M1g, expanding out the expression for Fg1. In the x direction, we have something new this time, not y, x. In the x direction, we have something new this time because now we have tension minus the force of friction equals M1ax. And we can expand this one a little bit because we know, since this is moving, there is an equation to calculate the force of kinetic friction. And that equation is mu Fn. Usually we would put a little k to denote that it's kinetic friction, but since it tells us that the kinetic friction variable is just mu, we're just going to leave it like that. Mu Fn equals M1ax. But we could even go further than that. Why might we want to go further? Well, Fn isn't allowed in our definition, or it's not allowed in our solution for the acceleration. So we might as well expand this out further. Good thing we just solved for Fn as being M1g. So ultimately, I can get my net force equation down to being T minus mu M1g equals M1ax. Now, we can't solve this for the acceleration right now because we have a variable that is not allowed in there, the t. Okay? Remember, tension in this case is going to be an internal force. It's a force between parts of the system. It's not necessarily an external force. Oh, so on that note, I guess the table is not necessarily an external part of the system as well. Our system is still just M1, M2, the string, and the pulley. Okay, for object 2, in the y direction, we have no forces, so F net y equals 0 newtons. F net x equals Fg2 minus tension equals M2 AX. So, expanding this out, we have M2G minus t equals m2ax. And now we see that we have two different equations with two unknowns, essentially, or one thing we're trying to solve for, but one variable that's not allowed. We're not allowed to have t in our expression. We're trying to solve for ax. So we need to solve one of these equations for t, in other words, get it into t equals form, and then plug it into the other equation. I'm going to choose this one. If I add mu mg to m1g to the other side, I get tension equals mu m1g plus m1ax. I'm going to plug that in over here. So I have m2g minus, that minus is going to get distributed to both of these terms, minus mu m1g minus m1ax equals m2ax. We need to get the ax's on one side. And once we do that, we see that we would have, okay, m2g minus mu m1g equals, I'm going to pull the ax out to the front, ax m1 plus m2. I'm going to divide both sides by m1 plus m2, leaving me at this. Ax equals m2g minus mu m1g over m1 plus m2. And that is the expression for the acceleration. Again, we could look at some limiting cases with this. What should happen if m2 gets really big? Well, then the denominator gets really big, and this gets really big, making these two terms negligible. The m2's cancel out. We get g as an acceleration. If we make m2 really big, the acceleration tends toward g. If we make m1 really big this time, we get something a little bit more interesting. We actually get an acceleration that should go towards 0. The reason for that is the bigger m1 gets, it almost looks, and maybe I shouldn't have said this one, it almost looks like it should tend towards a negative acceleration, but that doesn't quite make sense. That would mean that the acceleration is in this direction, which would never happen. What's really happening here is there's a limit to how big m1 can get, and we still have kinetic friction acting on this. So at some point, m1 would get big enough so that there would be no motion at all, and the system would remain where it is. But in either case, what I really want to look at is the top and the bottom again. This top part, and I guess we could factor out a g if we wanted to and put a g out here, but no real point to do that. m2g, we know, is the force of gravity on m2. Minus mu m1g. Where did that term come from? Well, it was here, and if we trace it back up, we see that it's the force of friction on m1. And it's interesting to note that, again, we have two different equations that are, or two different terms that end up representing the net force, the net external force on the system. Gravity on m2 tries to drive the system this way. The friction on m1 tries to resist that. There's no other external net forces in this direction, so we get that the net force is gravity minus friction. So that makes sense. And again, m1 plus m2 is just the total mass. So once again, we have net force, net external force, over total mass equals the acceleration. And it seems to make sense. Let's just plug in, just to make sure that we have the skills to do it. If m1 equals 8 kilograms, m2 equals 5 kilograms, and mu equals 0.2, calculate the acceleration of m1. We know the equation is ax equals m2g minus mu m1g over m1 plus m2. We substitute in. Let's see, m2 is 5 kilograms times 10 meters per second squared minus 0.2 times 8 kilograms times 10 meters per second squared, all over, this is 8 kilograms plus 5 kilograms. Okay. Doing the math, we've got 5 times 10 is 50. 0.2 times 8 times 10, let's see, that would be 0.2 of 10 is 2 times 8 is 16. Just to check. Yep, 16. So we've got 50 minus 16 over 8 plus 5 is 13, which is 34 over 13, which is a little bit over 2.6 meters per second squared. And this is something that we could test. If we had these masses and this coefficient of friction between one of the masses and the surface, and we had a pulley, we could actually test this out and see if the acceleration is in fact 2.62 meters per second squared. So this is just another example of a two-body system. You'll see a lot of these in our homework, or in our homework and in our examples in class. Make sure that you understand how to do these, because there's a lot of stuff, there's a lot of different things that go into this. It's one of my favorite parts to teach and to talk about and help students with. So if you have any questions, please make sure to ask me, as well as looking at the notes. And I look forward to going over problems like this with you in class. I'll see you later.